So the agenda of today, I'm going to talk about the motivation of our work, a bit of the background on the Markov decision process in the case when the state space is large, and also how we want to evaluate a heuristic policy in that setting. Then some background on the sampling-based algorithms that I investigated in this work. So I looked at sparse sampling UCT and FSSS, sparse sampling FSSS, and explain the way the technique that we use to bring these algorithms together to create a better performing algorithm, and finally the summary. So as Tze-Yun has explained in the previous talk, Markov decision process is a very elegant framework to formulate sequential decision making with uncertainty. And so in our case, when we want to apply this framework in real life settings, because of the complexity of the decision domain, usually we have very large state spaces, and usually in cases when the state space is continuous, it can be infinitely large. So classic approaches in solving MDPs can be mentioned as value iteration or policy iteration, and all of them are insufficient in the case when the state space is too large, because the running time of these algorithms usually grows with the size of the state space. And so to solve large state space MDPs, there are some viable approaches. In this work, we look at sampling-based algorithms, and the reason is that these algorithms have running time very independent of state space size. So even though you have very large state space, the running time won't be affected at all. But then the trade-off is that the running time is exponential to the accuracy of the algorithm. And that means that it can still be very large. On the other hand, we have some domain experts who can handcraft some heuristic policies to run in these domains. However, these handcrafted heuristic policies can be accurate and inaccurate at the same time. So in cases when the experts know, in cases when the expert has anticipated, he can craft the heuristic for those cases. But then in cases when he did not anticipate before, then it can be inaccurate. And the objective is to combine all these pieces of knowledge together to get a better algorithm with that has shorter runtime and has better performance. So a bit on the background, MDP formulation can be described as a tuple SATR gamma with say state S, action set A, next state distribution, and reward function T and reward function R. In this case, we only consider the case. In this way, we only consider the case when the reward function is bounded, as in there exists a number that an upper bound on the reward, and discount factor gamma to doubly temporally remote rewards. So in the MDP setting, an action policy pi is a mapping from the state to action. And this mapping can be stochastic or stationary or static, which means this can return one action or an action sample from a distribution for every state S. In some cases, like for example, in a video games or something, sometimes it's easier to obtain the simulator in place of the T and R reward functions, T and R functions. And a simulator in the setting is defined as a black box that returns a randomly sample couple next state S prime and reward R given the current states and the action. So given an action policy, people usually look at the value of the policy and V pi as S0 at a state S0 and the Q function. The goal of MDP is to find or to approximate the optimal policy pi star, which is which is defined as a policy that has the highest, that dominates, that has value that dominates all the policy. And we also define the required of the policy. In this case, is the required policy is as the epsilon optimality. If a policy is epsilon optimal, its value is not too far away from the optimal value. Now, given a heuristic policy, how should we use it to estimate the value of a node? And one way to do that is to just do repeatedly sampling B trajectories of length L from the current states that you're looking at. And by taking the average of the return reward, we can get an approximation that approaches the vicinity of epsilon 0 from the optimal value. And so this method approximation is fast, but then it also can be inaccurate because it can't really go very close to V star. It is bounded by that. And the idea is that the more trajectories and the longer the trajectories you do, the more accurate you will get. But then you can't really get to the V stars. Sparse sampling is an algorithm proposed by Kearns and colleges in 2002, and the idea is very simple. They build a look-ahead sample trees from. This is an online algorithm. So, given a current state, they just build a look-ahead sample tree by sampling for each action, sampling C times, and for the depth of H. This algorithm accuracy is approaches the optimal value, but then it is very slow. So if you look at the regret of sparse sampling, you can see that the majority of the times, like the accuracy is greatly dependent on the size of a tree instead of your estimation at the leaf node. So even though you can try to improve the accuracy of sparse sampling by having better approximation at the leaf node, but you might still not able to improve the accuracy of sparse sampling. So given a heuristic policy and sparse sampling, we want to bootstrap sparse sampling in such a way that the overhead is not too much, and we still retain the performance of sparse sampling. And so the idea is to add a heuristic estimated arm to each node in this tree up to a certain height, h hat. And so by doing that, we are incurring a small overhead, which can be tweaked so that is negligible. And so the accuracy of this method is still it still retains the same accuracy of sparse sampling, and so but the additional thing that you get out of it is that it will be able to propagate the heuristic estimation if it uses good estimate, and it is able to form back to base tree otherwise. And to evaluate this method, we use a few domains, and one of which is a video game that we built in-house. In this video games, the planner is to control two characters, the farmer up here and the dog here, and the goal is to herd the sheep into the pen while avoiding, while trying to prevent the wolves from attacking the sheep. And so with this kind of domain, if we have a lot of wolves and a lot of sheep, the state space will grow very large. One simple heuristic for this domain is to break it down into smaller subtasks in each of which you abstract away all other NPC or non-player characters on the map and then take the average of it. So the result we got is that even though on average the heuristic gives not good value, but then when we use that to bootstrap sparse sampling, it still gives some performance boost there. And so the x-axis is time per action, the amount of time set aside for the blender to run this algorithm. And we stop at 50 seconds because we actually look at the region around here, like up to 1 to 2 seconds. So UCT and FSSS are two descendants of sparse sampling, and the goal is to build a tree in a more in a better way. Instead of building the whole tree, they just want to sample this tree selectively. And so UCT, so the takeaway in this slide is that the time taken for each run out for UCT is OH, whereas the time taken for each run out in FSS is actually OKCH. So if we consider so if we fix a time for planning, then UCT should show to be able to converge faster, but UCT is known to be slow in escaping out of local maxima. And we use the Aux method to bootstrap UCT and FSSS, and it showed that there are improvements in performance. But then if you look closely at the graph here, you can see that UCT converges faster to a local optimum, whereas FSS is lower. But then eventually FSS will exceed UCT in terms of performance. So we wanted to find out a way to combine these two algorithms together. And the idea is to use normalized entropy to keep, so UCT converge on a local optimal when the frequency of selecting a local optimal arm is especially high as compared to the rest. And so the notion of normalized entropy allows us to detect that, and so the idea is to keep both FSSS and UCT running, but then we distribute runouts between FSSS and UCT based on the Bernoulli distribution, with parameter being H and P. So with this approach, we never stop sampling UCT and FSS trees, so convergence is still guaranteed. And the other property is that it is able to mitigate a negative effect of heuristic policy in UCT. And this problem has been discussed in a previous work of ours. So conclusion, in this work, we propose a simple bootstrapping method that is very easy to implement, unobtrusive, because we can just put a flag there. If we set to true, then we use also the Aux method. If we set false, we disable the Aux method. So it's very easy to put in and take off. And also, it has shown to be able to work with heuristic policy of unknown quality. And the second part of the paper discussed on techniques to combine multiple sampling-based algorithms together. That show good result too. So that's the end of the work. Hi.
Hi, sorry. So on some of your plots, the performance of sparse sampling, let's say here, doesn't matter, was plotted as a function of time.
Yeah.
And here I lost you because sparse sampling is a contract algorithm.
Right. So we actually implemented an iterative deepening version of sparse sampling. So we set a high edge, and we run it to the end. If we still have time, then we increase the height, and we rerun the algorithm again. So so when I talk about sparse sampling here, and in order to compare it with the rest of the algorithms, I had to implement an iterative deepening version of it.
But then, okay,
Yep.
I understand.
Yep.
But with iterative deepening, the time length of iteration increase exponentially.
Yep.
And somehow I don't see that in your plot. It looks like it smoothly increase almost linearly.
So
So
that's
for a long time, it should be flattened. And these regions of flat performance improvement should go longer and longer. And just look weird. I don't know.
So how should it look in here?
Like steps. Where?
Because
the x-axis exponential.
Yeah.
Right. Now I get it. Sorry.
Okay.
Questions? Alan?
So have you compared this to just doing one-step look ahead with the policy rolling out after that one-step look ahead? My experience with this sort of thing is often UCT will basically start out doing one-step look ahead with a policy, and then the variance just reduces, and you really never do better than one-step look ahead with a policy. Do you have anything to say about that, or any insights?
So what do you mean by one step look ahead?
So only build the UCT tree to depth 1, but you still do the policy rollouts.
Right. I didn't compare with that, but so I guess UCT, when I run a UCT algorithm, we will do that initially, but then after a while, it will build up the trees, right? So
Yeah, so if you haven't run it, you don't know, but
yeah.
the question is, does that building of the tree actually help compared to just, reducing the variance of the policy evaluations?
I see. It's a good question. I should go back and see whether and try that in our experiment.
I'll bet money that it will be about the same. But
Yeah. Well,
it's just a hunch.
so the improvement of UCT is not a lot in this case. So I think it would be roughly. But then, if we have a lot more time, then FSSS will be better.
I think that I will kind of join Alan's question because we saw exactly the same phenomenon in our experiments as well. Basically, when it looks like UCT is improving and whatever, they all improve, but it can be the case that they improve from a very, very deep hole. So achieving that performance at the end can be done like that, for example, with what Alan suggested,
One step.
just treating actions at the root, at the current state, as multi-arm value.
I see.
And that's it. No tree growing. And it's amazing. I mean, it's just really hard for UCT or its brothers to just hit the performance of this inaccurate, non-converging, whatever procedure. It's amazing.
Yeah, we sort of saw the non-improvement here. So if we have very little time, then the tree will not be grow very large. But we have larger time, the tree will grow larger. And so in this case, you see that the improvement is very little. And that's why we investigate the FSSS, because FSSS has a nicer kind of improvement when we give more time to it. And so given the fact that we want to have something really good initially, this region, that's why that brought us to trying to combining them both together. But yeah, I actually observed that the improvement is really, really negligible. Yeah.
Okay, just one final quick question. You've only experimented here with sheep farmer. Have you looked at results in other domains?
Another one. So in the paper, we investigate also the domain. It's called obstructed selling.
Okay.
So it's just the
The only one I
selling
would
in the
suggest is there are 8 benchmarks that Carmel and others have been experimenting on, and
Right.
that are quite varied. And you might want look at a larger set of benchmarks. I'm slightly afraid you've drawn too many conclusions from 1 or 2 domains.
Right. Yeah. So we wanted to create a game AI for the game that we are building. That's why we wanted to make sure that it works for the game. So it was the focus of our work. But then you're right. So in one of the feedback I got from people is to investigate this in the domain of chess, for instance, or the Go.
Okay.
Yeah,
Or
but-
look at Cornell's papers now, there's where they've looked at many other
Yeah.
domains.
Yeah.
Okay, let's thank our speaker.